I mean, quantum mechanics has, I suppose, grew out of an attempt to describe matter, the structure of matter, to understand atoms and molecules. Although it's worth saying that atoms and molecules, in the way we conceive of them today, were not known to exist, or the structure of them was not known in 1900. That comes a little bit later with the discovery of the atomic nucleus and so on. But the idea that matter is made of smaller things can be traced back, of course, philosophically to the ancient Greeks. But there's a beautiful book by Johannes Kepler. So Kepler's probably most famous. I'm sure you've heard of the name in the context of the laws of planetary motion, which laid down the foundations on which Newton built his universal law of gravitation. But there's a beautiful book that Kepler wrote in 1610 called On the Six-Cornered Snowflake, which to me really illustrates the genius of Kepler. And it's a sort of meditation on patterns in nature. So the story, as Kepler told it, he was walking across the Charles Bridge in Prague in a snowstorm, going to a party at his benefactor's house in the castle. And he realized that he hadn't bought him a present. He hadn't brought him a gift, a New Year's gift. And so he noticed, he started thinking about the snowflakes landing on his arm. And of course, when you look at a snowflake in some detail, you notice that whilst they're all different, there is a similarity to them. There's a sameness, a sixness to them, some kind of symmetry that they all exhibit. And so that got Kepler thinking, why would it be that these things, these snowflakes that fall from the sky, all share this similar structure? And I find it wonderful that he in that book, he essentially says that it must be something to do with the building blocks, that there must be some underlying reason why nature has this symmetry. And then he goes on to think about pomegranate seeds and beehives and all sorts of things and hexagons in nature. But it really, what you're glimpsing there, and Kepler said in the translation of the book, in the English translation, there's this wonderful line at the end where he says, I'm knocking on the doors of chemistry. So I'm not sure where that translation comes from, but it's correct. What he's noticed is that symmetry is, he saw that it was something to do with the building blocks. We now know it's to do with the water molecule. So the shape of the water molecule, H2O, two hydrogens bonded to an oxygen in a very famous shape, which kind of goes like that, which you can calculate now from quantum mechanics and the way the electrons are arranged around the oxygen and the hydrogen and so on. Of course, he didn't know any of that, but I think it's genius, really. You see in that book, I strongly recommend it, the genius of Kepler. Quantum mechanics it grew out of an attempt to understand some curious experimental findings, which actually at the time weren't considered to be so problematic. There were questions about the colour of light or the nature of light emitted by atoms. So very famously, for example, sodium vapour. If you remember old sodium vapour streetlights, and they glow kind of yellowy orange. And the question was, why? So there's the colour of light from atoms. The origin of quantum mechanics, though, probably can be traced to Planck's explanation of the way that hot objects radiate. So 1900, the late 1890s, 1900, there was a problem with the calculation of how a hot object radiates in terms of the wavelengths of light that it emits and the calculation. Essentially, the calculations of the wavelength of the light from hot things were just wrong. And in 1900, Max Planck made a revolutionary proposal. I've read in some biographies of Planck that it was essentially a leap of genius, almost inexplicable. But he famously came up with the idea that a hot object only emits light in little packets, which subsequently we came to know as photons following Einstein, but that was much later. So it's this idea that a glowing thing doesn't just emit light at all wavelengths and radiate all sorts of light, but it somehow, for some reason that was not known to him at the time, emits wavelengths, radiation in little packets. And so that was a huge leap. And actually, he didn't really, at the time, think that he thought it was a calculational device. But what's important is that the fundamental constant of nature that we associate with quantum mechanics, now known as Planck's constant, appears in the calculation. And so very specifically, Planck found he was able to describe the experimental data if he assumed that light is emitted in little packets, and the relationship of the energy of the little packet, the photon as we would now call it, to the frequency of the light is E equals hf, where f is the frequency of the light, E is the energy of the packet, and h is this new constant of nature that we now know as Planck's constant. So I would say that's the beginning of modern quantum mechanics. So when Planck introduced photons, as we would now call them, well, you get the sense that he certainly didn't believe that this was real, that light, the electromagnetic field, really came in little packets. He thought it was something to do with perhaps the way matter oscillates, like little oscillators, we call them now, harmonic oscillators in the stuff that emits the light. It was something to do with that, kind of a mathematical trick. He didn't, certainly at the time, think that what was being implied was that light really can be pictured as a stream of particles with an energy proportional to their frequency. He didn't think that at all. Einstein, in 1905, wrote a very beautiful paper for which he subsequently got the Nobel Prize. This is the same year that he wrote the special theory of relativity and a very famous paper on Brownian motion. But it's the theory for which he was most, I suppose, well known at the time. It's a theory of something called the photoelectric effect. So the photoelectric effect is, again, it's an experimental observation that if you shine light on a piece of metal, let's say, some substance, then the light can hit the substance and cause electrons to be emitted from the substance, from the metal. But what was observed was that if the light is too long a wavelength or too low a frequency, then no matter how bright the light, then you can make it brighter and brighter and brighter and brighter, no electrons are emitted. This is a mystery. If you think of light as just delivering energy to something and just a not like a stream of little particles, then it would seem that if you turn the intensity up, brighter light, then you'd supply enough energy to knock the electrons out of the metal. That's not what happens. So you find that there's a minimum frequency. Remember, the frequency is the color. So it's almost like saying, if I shine red light on this thing, then no matter how bright the red light is, nothing happens. But if I make the light a little bluer, you get to a point where electrons start coming off. And then that light can be quite dim, but it will still emit electrons. So this was a mystery. It's called the photoelectric effect. Einstein explained it following Planck by saying that actually you can think of light as a stream of particles, photons. And then if the photons don't have enough energy to knock the electrons out of the material, then no electrons will emerge. So you could imagine just having one single photon, but if it has enough energy, then it will come in and knock an electron out. And so that's essentially the photoelectric effect. It's important because it's the first time that we get the sense that this so-called quantization of the electromagnetic field, this chopping up of light into little packets, is not to do with the way that matter emits light. It's to do with light itself. The idea, it's going all the way back hundreds of years to pictures that Newton would have had of light being a stream of particles, that you can really think of these things called photons, almost like little bullets that go and hit things and interact with them. So that's 1905. And it's worth saying, actually, historically, that was very controversial at the time. You really get a sense when you read the papers of the time, that people thought that this was a calculational device or something to do with matter and not to do with the electromagnetic field itself, not to do with light itself. And actually, there's a very famous letter of reference that Planck wrote for Einstein years later. It's in the 1910s, I think. So 6, 7, 8 years later, recommending him for a position, for an award. And Planck said that Einstein's belief in the reality of photons should not be held against him. And this is years after the 1905 paper. So it gives you a sense of the intellectual struggle that quantum mechanics and these early ideas of quantum theory caused, the intellectual problems that it caused for people at the time. And I always remind my students of this when I teach introductory quantum mechanics. One of the key things, it's not so mathematically difficult, at least in an introductory presentation, but the ideas themselves are profoundly counterintuitive. And that's why it wasn't the mathematics really, that's why it took decades from these early glimpses of quantum theory at the turn of the 20th century for a coherent theory to emerge, arguably in the 1920s. And then you could argue that even today, the interpretation of what the theory is telling us about the nature of reality itself is not universally agreed upon. One of the big changes actually that's happened in teaching quantum mechanics in universities over the last few decades is that it was always, when I learnt it, so back even in the 1990s, it was common to teach it historically. So you go through the things that we've talked about. You go through the photoelectric effect and the structure of atoms. You get to Niels Bohr and his early explanations of how atoms might work, following on from Ernest Rutherford in Manchester detecting the atomic nucleus. And so this idea that an atom is a nucleus, a dense positive charge. It wasn't known exactly what the structure was at that time, with electrons, let's say, orbiting, in inverted commas, around it. So that there's a picture of almost like a solar system, but it was known that doesn't work because you have charged particles moving in the vicinity of other charged particles, and that means that they radiate and they would not be stable. And so there's all these things going on, confusion, and then Bohr suggests that electrons can only take certain energies, which we now call orbitals, around the atomic nucleus, and all this stuff is going on. And it used to be that we would teach it like that in university. But if you do that, you pick up all the confusion, the confusion, decades and decades of confusion that these great physicists felt in trying to come to terms with this counterintuitive picture of the world. So now, I think it's more common in universities to start with the theory as we understand it today and just say, well, this is the way the world works. And perhaps the best introduction would be to think of a property of particles called spin. So you might call these things a qubit. So what is a qubit? So you think of a coin, which you would toss in the air, and it can be either heads or tails. So that's a kind of an intuitive picture of the world. This thing is either heads or it is tails. Now, a quantum coin could indeed have the property that it would be heads or tails. But the difference between quantum mechanics and classical theory is that an object like a coin, a quantum coin, can also be in what we call a superposition of heads and tails. So that means that it can be in a state where it is, let's say, if we observe the thing, we'll talk about that a bit later, but it can be in a state where it could be 30% heads and 70% tails, or 40% heads and 60% tails, or any combination, any mixture of heads and tails. And that is a perfectly legitimate description of the state of the configuration of this thing. Just to give you a sense of a real physical object that would behave that way, particles like electrons, for example, have a property called spin, which can be up or down. It's like heads and tails. But that's the key thing that objects like electrons can not only have definite values of some property, something that you can measure, but they can be in a mixture of those things. And it's not a probability theory in the sense that we would usually think of probability theories. So usually we'd say, well, there's a 50% chance it's going to rain tomorrow. Why do we say that? Why we would say such a thing? It's because we have incomplete knowledge of the system, in this case, the weather. And so we have incomplete understanding of where, I suppose at the most basic level, all those water molecules are in the clouds and so on. But we don't have enough knowledge to precisely calculate what is going to happen. And so we assign probabilities to it, which that reflects our ignorance of the situation. The key difference in quantum theory is that these probabilities are fundamental. They are fundamental to the description of nature. So it is not the case that if we have an electron in some kind of configuration, then our theory predicts probabilities because we don't quite know exactly how this thing is configured. The probabilities are intrinsic to the theory itself. And pretty much all of the intellectual challenges and the confusion around quantum mechanics comes from that very simple property.